And this is
Okay, and this next talk, before we have another coffee break, will be given by Bernhard Gittenberger on the number of graphs with twin width 1.
Thank you very much, and thank you for the organizers for the opportunity to present this here. This is, can you hear me? Yeah, okay. This is a joint work with Zbyszek Gołębieski, Małgorzata Sulkowska, and Michael Wallner. And okay, let us start. Historically, there is a concept which is well known for graph theory, which is a tree width, which somehow measures how far a graph is from the tree, and it has some algorithmic implications. But there is another simple graph. Well, trees are simple graphs, and that's why the tree width is so important. But there is another class of simple graphs, which is cographs. The cograph is defined as follows. You start with a single vertex, then you apply operations like disjoint union and join. So for instance, start with a single vertex, then copy that single vertex. Now I have two cographs. The disjoint union is just this. Take this again, but this time the join of the two. So you connect it by a single edge. Then the join of these two is this, and so on. Now take the join of that, then another cograph. Now the disjoint union of this, another cograph, a single vertex, and the join with the other. So this is an example for a cograph. Cographs have certain nice properties. For instance, the join operations can be replaced by complementation. So disjoint union and complement, that gives you the same class of graphs. And cographs can be reduced to a single vertex by iteratively deleting twins, where twins are vertices that have the same neighborhood up to their own adjacency or not. So for instance, these two are twins. So we can merge these two, and then we get this. Now we have found two further twins. The neighborhood is these two, the black ones, and they are adjacent, that count. So the red one doesn't count to the neighborhood in that sense. So these two red vertices are again twins, can be merged. Now another two twins, merge them, merge them, merge them, and finally merge them. And every cograph can be reduced in that way.
Is that a characterization of cographs, or is
yes? This one, the last. Yeah, yes, that's it. Yeah. And now one is interested, how far is a graph from a cograph? So therefore, the several concepts must be introduced, and in the end, the twin width. But first, we need to define a trigraph. A trigraph is a triple of a graph, VE, so vertices and edges. Additionally, with a separate set R, which is a set of so-called red edges. And each red edge may connect non-adjacent vertices of V. Okay. And then there are contraction rules for trigraphs. So if you have two vertices, then, this one. If you have two vertices, then you look at the neighborhood of these two vertices. So the neighborhood of the two vertices in common, so that stays the neighborhood. These are these three vertices here. This vertex is a neighbor of one of those, but not of the other. And the same applies to the other here. So they are all neighbors of one of the two vertices, but not of the other one. Then you may merge these two vertices, but neighbors of both, they stay neighbors of the merged vertex. Neighbors of exactly one of the two, they become kind of special neighbors connected by a red edge. And if you had already a red edge present among the connections to the neighborhood, like here, then that stays a red edge. So here, this is a red edge between this vertex and a neighbor. Though this has a black edge here, the red one wins. So in the merged vertex, it stays the red edge to this vertex. So these are kind of contraction rules that can be applied on trigraphs. So in a trigraph, every vertex has two kinds of degrees, namely the ordinary degree in the graph and a red degree where you count only the red edges. And now, if you have a graph with n vertices, say, and you regard this as a graph with 0 red edges, then you can apply these contraction rules for trigraphs iteratively, one by one. So you get a sequence of graphs. Sorry, I have to get used to this. You get a sequence of vertices, as a sequence of trigraphs, where the first trigraph is just the original graph. So we start with the full vertex set, and the one with number k. So we go from k down, from n down to 1. The kth vertex set has only k vertices because in every step 2 vertices are merged. And this sequence is called a decontraction sequence if for all those trigraphs, no single vertex has more than d red edges incident to it. This is a decontraction sequence, and the twin width of a graph is defined as the minimal d that is possible for a decontraction sequence of the graph. So for instance, let us look at a simple example, namely cographs. In cographs, you may always have twins and merge them. And as they have the same neighborhood, there is no red edge appearing from this merging process. So cographs have twin width 0. And in fact, this is a characterization of cographs. Another example, the P4, the path with 4 vertices, you may contract it, for instance, contract the 2 middle vertices, then the neighborhood differs in both. Here 1 and 4 are neighbors of only one of the two, so you get 2 red edges in that way. But you can do it in another way by merging 1 and 2. Then the only difference is in the vertex 3. Which is a neighbor of 2, but not of 1. So you have 1 single red edge. Now merge 2 and 3. These red edges wins over the black red edge, and finally merge totally. So you have a 1 contraction sequence found for the P4. And if you do it in another way, like merging 1 and 3, then it's also a 1 contraction sequence where you always have only red degree at most 1. And this is all by symmetry. You can more or less, you end up with one of those cases. So less than 1 is not possible. So the P4 therefore has twin width equal to 1. Okay. Now, some facts about twin width. As I said already, cographs are exactly the graphs with twin width 0. Then bounded twin width, there's a lot of classes where it was shown that the twin width is bounded, like for proper classes of permutation graphs, for interval graphs, for planar graphs. One has shown, for instance, that the twin width is at most 8, and that there exists a graph, planar graph with twin width 7. So it's not clear where's the best bound so far. Graphs defined by forbidden minors have bounded twin width, and graphs with bounded tree width have bounded twin width, but these graphs can be exponential. Well, the twin width can be exponential in the tree width. Then there are also algorithmic implications like model checking. First order model checking is fixed parameter tractable for bounded twin width instead of NP complete for general graphs. And also a lot of optimization problems which are NP hard or NP complete become fixed parameter tractable for bounded twin width graphs. So this also has algorithmic applications or implications for graph theoretical, for classical graph theoretical algorithms.
There must be something wrong with the interval graphs. I think there's also proper subclasses, right? There's too many interval graphs. Twin width, bounded twin width means small. So I think there's too many interval graphs.
Okay. Maybe proper classes. Yeah, maybe. Copy paste error. Maybe I don't know either. So what is a permutation graph? There was already mentioned that are graphs that can be represented as a permutation diagram. So for a pair of permutations on the vertex set, so let us look for an example. Let's take two permutations on 6 elements, sigma and tau, and then write in 2 lines the permutation sigma in the top line. So these are the values of sigma here. These are the values of tau, and then connect the sigma to the -1 of L point and the tau to the -1 of L point. So these 2 points for each L between the 2 lines, then you get such a diagram. And how is this to be read? So you see that we connect all the vertices here that have the same number. They correspond to a vertex of a graph. And whenever 2 lines cross, the 2 vertices are adjacent. So this diagram is actually, so yeah, this is written what I just said here. And they are adjacent if and only if they are an inversion of this permutation here. And this gives this graph. So this is a permutation graph, and every graph that can be represented in such a way is a permutation graph. Then what else is needed? We need the concept of a module of a graph. A module of a graph is a graph where every vertex that is outside the module is either connected to every vertex of the module or to none of the vertices of the module. And then we need also the concept of a splitter. A splitter is a vertex with respect to some set W, subset of the vertices, such that it is connected to some of the vertices of W, but not to all of them. So obviously, a module cannot have a splitter. So if you look at our graph here, the permutation graph from the previous slide, then the colors are corresponding to the module of that graph. And for instance, the vertex 6 is a splitter for the set 1, 2, 3, because it's neighbor of 2 of them, but not of all of them. And then we need prime graphs. Prime graphs are graphs which have only the trivial modules, namely the single vertex sets and the whole graph. And strong modules are such modules that are not inside, well, they do not overlap with another module. So either they are contained in another module is contained in them, or they are, or no, that's nonsense here, or they are disjoint. So that's what should be written here. And modules always correspond to intervals in permutation diagrams for permutation graphs. So some results, why did I tell you about permutation graphs? Because every graph with twin width at most 1 is a permutation graph. There is also an algorithm that kind of detects in linear running time that a graph has twin width at most 1. And this algorithm also constructs a witness, so a one construction sequence that shows that it indeed has twin width 1, or at most 1. And finally, it is also shown that if you use the modular decomposition of a graph, then the above theorem extends to all graphs and not only prime graphs. Okay, why did I tell you that? Because we want to use this algorithm and kind of reverse engineer it in order to count, or at least to give a bound on the number of twin width 1 graphs. So first of all, let us look at how the algorithm works. It can be shown that one of these extremal vertices, as they are called, so at the end, is a splitter such that the construction sequence ends with that splitter. So the algorithm starts with that splitter and removes it. So let's do it. And then it defines some sets A and B and C that are maintained during the algorithm. So the splitter kind of splits the lower line here into intervals A and B, and one interval on the upper line. And now you are looking for doubly extremal vertices, so that are kind of on the boundary of two intervals, like this one. So this is doubly extremal because it's on the end of A and at the beginning of C. Such vertices are removed. Now look for the next doubly extremal vertex. In this case, this is not doubly extremal apparently, and this neither. So we cannot continue. But if one of the sets A and B has only a single element, you can continue, namely take this single element as a next splitter. And this is, in this case, we can do that, remove it, and redefine ABC. And now continue. Find double extremal vertices. So there is one, remove it. There is another one, remove it. Another one, remove it. Now with 10, we cannot continue, but we can now swap to the other side. 7, we can remove it. 9, we can remove it. 10, and so on. So, and if we end up with this diagram, then the graph has twin width at most 1. Otherwise, it has not. So, furthermore, in case of a twin width 1 graph, we can always start with this splitter, as I said, and then A and B are non-empty if we do that. So there is another algorithm looking for twin width 1 graphs which can be exploited, and where we can get a big O of 8 to the n by investigating this algorithm, which was shown by Bonnet et al. In 22. But we want to improve this bound using this algorithm I just showed you. And what we show, so this bound can be a little bit improved, well, exponentially improved actually to this value here as exponential basis. And for the number of unlabeled graph of twin width 1, not necessarily prime graphs, we also get the bound, which is a little bit larger, as the exponential basis close to 9. And we also have a lower bound. Well, there is still a big gap, but okay, at least we have some interval where this kind of number lives. Okay, now how do we do that? We kind of do the reverse of the algorithm. So that means we start with one of the initial configurations, which is one of those. And then we have either defined already A, B, C, and all of them are non-empty. And then we can continue in some canonical way, or we have just opened A and B is still empty, and we have to continue in some other way. So let's say we start with one of those configurations, and then we grow C, say, to the left. In the end, we want a big O of something to the end. So whether left or right, that doesn't really count so much here. And then we have 3 phases of the construction process. First, only A is grown. So that means you grow C to the left, and at the same time you grow A, and B is still empty. Of course, if you start with one of those configurations, then this phase is skipped. Second phase, you start to open B. So one of the vertices that grows the set C is also going to B. Then B is open, and then this phase ends with a splitter. And third phase, we add left-right segments to C, add a splitter, and iterate the whole process. So it turns out that the first 2 phases are asymptotically irrelevant. So they are small. So that means we need to concentrate on the third phase, because there kind of the main asymptotics come from. So let's look at this. After the first 2 initial phases, our diagram certainly looks like this. So we have constructed a set C. Then we have opened also the set B. So that means we have some elements in A, some elements in B. And then we finish the whole phase by adding a splitter. So a splitter is an extremal point that is not doubly extremal. So that is kind of between, that kind of defines, when the algorithm comes to this, it removes the splitter and defines and redefines A, B, C. So it separates here A and B. So that means the algorithm comes from a situation like that. So there was a splitter detected as a single element in one of the two sets A and B that is removed and separates the set on the bottom line. So that means the next step would be to redefine A, B, C in that way and then to continue. So let P be the combinatorial structure of those permutation diagrams, and A, J, and C the combinatorial structures for the three phases. And we need to concentrate only on C. So we have P is just this product where the generating function is therefore also this product of Ij and P, Ij and C, sorry, this is a C. And the dominant singularity comes from that C, as it turns out. So we concentrate only on this. All right. So therefore, we define some combinatorial structures that are needed in order to describe the whole process. So if we are in some intermediate stage of the algorithm, the diagram looks like this. And we have here boundary points. A1, A2 are the two endpoints of A, and B1, B2 are the endpoints of B. And just for kind of to pinpoint where we are, I use these names for the atoms, where in fact it's only important that they are atoms. So we need a sequence construction of atoms A, all of them, all of those fours. So that means we add some vertex to C and we add one of those points, so at one of those sides of A or B on the bottom line. So this corresponds to a sequence construction on the atoms described here. Sometimes we need non-empty sequences. This will be the splitter construction when we add a splitter. And this is a generic adding of left and right sequence iteratively to C. And this is non-empty. Huh? So these are kind of auxiliary constructions. Then first lemma, so G is in fact the generic segment construction. So just remember what it is. It's a sequence of sequences, and the first sequence is using only 3 atoms, namely, say, without loss of generality, the first 3 here. Then there is a single element, an atom, and then there is a generic construction without restrictions. So N for no restrictions, you can use all of those 4 here. So why that? Because if the algorithm, if you start to add some segments to the left here, then of course, the algorithm was processing a right segment before, then it was removing a doubly extremal vertex here, and then it gets stuck here. Why get it stuck? Because this is not doubly extremal. So that means you must put something here in this subinterval in order to make the algorithm get stuck here. So there must be some T that blocks our last vertex here. And therefore, in the first phase here, you have only possibilities to go here, here, or here, but not here. Then once you start to block, and afterwards you are free to do whatever you want. So this is before the adding, you have a sequence construction with only 3 possible atoms. After, you have a sequence constructions with no restrictions. And in between, you have the T. For having a splitter added, S is the generic way to do so. Why? Because you can add a splitter after you have completed a segment. So that means this is just adding a single atom. This is this here, because there is no problem further. Because D is already blocked by T, and that's all you need in order to force the algorithm to go to the other side and remove the splitter. So we find S as the next splitter, add S by construction, or simply remove it when the algorithm goes to this. Second case, you go to the other side. So then there is something to pay attention of, because you completed the algorithm kind of sees the splitter on that side first, removes it, and before it, well, no, that the algorithm comes from before removing a splitter. A, B, C were differently defined. So C was the set here, B was the set with the single S here, because then that's why S becomes the splitter. and A was the rest here. And the algorithm was processing C. And so that means it cannot continue with C and must now find that splitter. So that means it could continue if this vertex would be doubly extremal. So that's forbidden and that's forbidden. That's why the last step in the segment here is not completely free, but you have only two choices. Oops, not written here. And therefore we have, if we go to the previous slide, therefore we have this, this expression here. So we have a last element with only two choices, and then you add the actual splitter. All right. And now the construction C is now simple because we have, well, you can add to the set C, you can add a left and the right. And the left, well, they are isomorphic actually. So either you add a splitter immediately, so add a splitter immediately, or you add a segment to C with at least one vertex. Then you can do a single segment and properly either with the splitter or change sides, and then you have this restriction at the end and the splitter afterwards. Or finally, you have at least two segments, then you have a non-empty segment, and then you continue the generic construction at least once, and at the end you end with the splitter. And now this can be, I'm finished in a minute, yeah. Now this can be translated into generating function quite easily, and you get C of Z is a simple rational generating function with a simple pole at some value here. And so the number of prime graph between with at most one is bounded by the inverse of this pole to the n. Yeah, and I think as my time is running out, I cannot do for general graphs. You use the modular decomposition for general graphs, and then you can kind of insert into the modular decomposition the bounds we have already, and get another function that describes more or less a sequence of upper bounds for the numbers of twin with at most one graphs without the side condition that they are prime graphs. Again, this has a simple pole, and this gives you that. And for the lower bound, I have nothing.